Hi, my name is Srinivasan, and I want to tell you about a recent result in algebraic circuit complexity with my co-authors Nutan Limay and Sebastian Davanas. Let me start off with a basic introduction to algebraic circuit complexity. So in the setting of algebraic circuit complexity, we deal with computational problems that have a specific form. So the basic setup is that there's a multivariate polynomial P, and the computational problem is to evaluate this polynomial P at a given input. And the way we go about doing this is by starting with the input and repeatedly applying elementary operations, which in our case are just additions and multiplications. Okay, so there's a lot like Boolean circuits but instead of Boolean operations as your elementary operations, we have additions and multiplications. Okay, and just like in the Boolean circuit setting, we have a notion of size, which is the number of these elementary operations, and a notion of depth. Yeah, but in the algebraic circuit setting, it's sometimes more convenient to look at this notion of product depth, which is just the maximum number of product gates on an input to output path. So it's equal to a depth up to a factor of 2. Okay, so the basic motivating question in algebraic circuit complexity is to find explicit polynomials that have no algebraic circuits of small size. Yeah, and so the algebraic circuit model is sort of more restricted than the Boolean circuit model because the circuit is supposed to represent the formal polynomial P. So it's a more syntactic model of computation. So it's expected that the problem of proving algebraic circuit low bounds is easier than Boolean circuit low bounds. And this is indeed, there is some formal justification to this, right? But nevertheless, despite this, in algebraic circuit complexity, we have not really been able to replicate all the successes of Boolean circuit complexity. So in particular, for example, you can consider the famous constant depth Boolean circuit lower bounds from the mid-80s. So we have exponential lower bounds for constant depth Boolean circuits since then, but we don't yet have such lower bounds for algebraic circuits. So in a paper last year, we were able to prove the first super polynomial lower bounds for general algebraic circuits of constant depth. Okay, so now we have super polynomial lower bounds, so that's good, but we still don't have exponential. And this work is sort of motivated by the techniques that we introduced in this paper from last year and seeing how far these ideas can go. Okay, so that's the basic setup. And so what I'm going to do now is I'm just going to dive into the proof of this result and tell you a little bit about it before I tell you what the results that we prove in this paper. Okay, so what do we do in this LST21? So in this paper, we look at, again, multivariate polynomials and the complexity of multivariate polynomials, but we'll be restricting ourselves to multivariate polynomials of a certain kind. Okay, so these are called set-multilinear polynomials. So what's a set-multilinear polynomial? So you have a set of variables, maybe you call it X. So this set of variables is partitioned into D sets of variables. So X1 through XD are D disjoint sets of variables, partitioning your overall variable set. And a set-multilinear polynomial is a polynomial where each monomial has a certain form, which is to say that it contains exactly one variable from each of these variable sets. Okay, so that's a set-multilinear monomial, and a set-multilinear polynomial is a linear combination of such monomials. So many naturally occurring polynomials are already set multilinear. So an important example is the iterated matrix multiplication polynomial. So here you're multiplying D n by n matrices, and the polynomial that you want to talk about is an entry in the product of these D matrices, right? So each entry is a polynomial in the entries of these matrices, and you can easily check that it is in fact a set multilinear polynomial. Okay, so that's the iterated matrix multiplication polynomial. Another important example of a set multilinear polynomial, at least for the purpose of this talk, is the so-called product of inner products polynomial. Okay, so again, you have D variable sets. Let's say each of them has size n, and you partition these D variable sets into pairs, right? And you think of each variable set as a vector of variables of size n, right? And you take the inner product of variable of the vectors in each pair, right? So you take the inner product of x1, x2, x3, x4, and so on, and then you multiply them all together. Okay, so that's the product of inner products polynomial, again, set multilinear. All right. So when you're looking at set multilinear polynomials, it's very natural to also look at a restricted kind of algebraic circuit for computing such polynomials. And these are called set multilinear circuits. Okay, so what's a set multilinear circuit? So it's a circuit where all the intermediate polynomials that are computed are themselves set multilinear. Okay, they may not be set multilinear in all the variable sets together. They may be set multilinear in a subset of these variable sets, but they are nevertheless set multilinear. So that's a set multilinear algebraic circuit. It's a restricted kind of algebraic circuit. So the reason that these circuits are interesting is that in certain situations, especially in the situation where the degree of the polynomials that we're looking at is small in comparison to a number of variables, it turns out that set multilinear circuits, general algebraic circuits can be converted to set multilinear circuits without a significant blow up in size. Okay, so you're going to take a general algebraic circuit and convert it to a set multilinear one without a significant blow up in size and a factor 2 blow up in depth. So what this implies in the contrapositive is something very interesting. So it implies that if you can prove a strong enough set multilinear lower bound for circuits of certain depth, then you get lower bounds for general algebraic circuits, maybe at a depth which is somewhat smaller. Okay, and we use this idea. So what we do in this paper LSC21 is that we actually prove set multilinear lower bounds, and then we use this simplification, which is sort of implicit in some earlier works and kind of generalized in our work, to get lower bounds for general algebraic circuits of constant depth. Okay, so how do we prove these set multilinear circuit lower bounds? This is the interesting question. And so this kind of goes back to an old lower bound technique in algebraic circuit complexity, which is called the partial derivative method. Okay, so this is due to Nisa and Victorson in a famous work from the mid-90s. So what do we do here? So again, we have a space of set multilinear polynomials, right? And now what we do is we sort of partition the d variable sets we have into two kinds. Okay, so I've colored them gray and green. You can call them row sets and column sets, whatever. Okay, so I'll just call them gray sets and green sets. So given such a partition of the d variable sets, what we do is we define now a matrix associated with this polynomial P. And this matrix is called the partial derivative matrix, and it's defined as follows. So the rows of this matrix are labeled by set multilinear monomials over the gray variable sets. So they're labeled by set multilinear monomials over the gray variable sets. So gray monomials are called them. And similarly, the columns are labeled by set multilinear monomials over the green variable sets. So the columns are green monomials. And now note that the product of a gray monomial and a green monomial is a set multilinear monomial in all the variable sets together. Okay, and so now in the entry corresponding to a row labeled by a gray monomial and a column labeled by a green monomial, you put in the coefficient of the product of these two monomials in the polynomial P. Okay, so each entry of this matrix is the some coefficient of the polynomial P is a coefficient of this monomial. Okay, so that's the partial derivative matrix of this polynomial. And the rank of this matrix is a notion of complexity of P. Okay, so it's what we use to measure the complexity of this polynomial P. So ideally what we would like to show is that if this matrix has large rank, then P does not have small algebraic circuits of some depth. Okay, so Nisa and Victorson used this to prove many interesting results, but in general, you cannot use this notion of complexity to prove strong constant depth lower bounds, even for set multilinear circuits. Okay, so this is an interesting fact, and it's kind of worth understanding. So let me show you this by example. So let's look at the product of inner products polynomial. Okay, so again, you have d variable sets, you pair them off and you take the inner product between each variable set and you take the product of all these inner products. Okay, so imagine that each pair of variable sets, so each pair of variable sets contains one gray variable set and one green variable set. Okay, and then when you take this product, of course, you have in each pair one gray and one green, etc., etc. Okay, so in this case, and it's not hard to argue that the matrix, the partial derivative matrix of this polynomial, is just a tensor product of the partial derivative matrices of these individual inner products. Yeah, and it's also not hard to argue that these individual partial derivative matrices are just the identity matrix. Okay, so the partial derivative matrix of the product of inner products polynomial is just a tensor product of identity matrices, and in particular, this has full rank. Okay, so we introduced this notion of complexity, and for this polynomial, this notion of complexity is as large as it can be because the partial derivative matrix has full rank. All right, and it's also not hard to see that this polynomial has a small set multilinear circuit of constant depth. Okay, this is what the circuit looks like. So it does what you would expect. So it just looks at each of these inner products, and you construct a circuit for that, and then you take the product of these circuits together, and you get a circuit for the product of inner products. Okay, so this is a small set multilinear circuit for this polynomial. All right, so this measure by itself is not strong enough to prove set multilinear lower bounds seemingly. So then what do we do? So what we do is we kind of make a small modification to this measure in some sense that forbids examples of this kind. Okay, so and that's enough, it turns out, to prove lower bounds for set multilinear circuits of constant depth. Okay, so what is this small modification? It's extremely simple. To be able to define these inner products, you do need that these gray variable sets and the green variable sets have the same size. So we just forbid this in the space of polynomials that we look at. And that's the very simple modification that turns out to give stronger lower bounds. Okay, so the setup is as follows. Again, you have a space of set multilinear polynomials. We'll call them lopsided spaces now, in order to emphasize that we allow these variable sets to have distinct sizes. Okay, so previously I had not said anything about them. In the product of inner products case, in fact, they did have the same size, but now I'm explicitly allowing them to have different sizes. So each xi has size from n to the rho I, and you should think of rho I as a parameter between 0 and 1. So this is a power of n that's between 0 and 1. Okay. So that's what it looks like. So that's what happens to the gray variable sets and green variable sets. They all have different sizes now. And what we showed in this paper is that we showed that for suitable lopsided spaces, small set multilinear circuits cannot compute full rank polynomials. So by the simple modification to the to address the PIP example, we actually get that the partial derivative technique is strong enough to prove lower bounds for general constant depth circuits. Okay, and what kind of lower bounds do we get? Well, we get a lower bound of this form, so it's kind of ugly. It's kind of an ugly expression. It's n to the d to some exponentially small function of the depth delta, but that's a kind of lower bound we are able to get for product depth delta. Okay, so this is not a very strong lower bound. Recall that d itself is a small function of n, but nevertheless, as long as d is a growing function of n, this is a super polynomial lower bound for every constant depth. Okay, so that's sort of a recap of the LST21 result. So using these lower bounds, we're actually able to prove lower bounds for certain very explicit polynomials, like the iterated matrix multiplication polynomial. Okay, so by restricting this polynomial suitably, we can actually find that it restricts to polynomials that are full rank and lie in these lopsided set multilinear spaces, and that gives us lower bounds for this polynomial. And now a natural question to ask given this is, are these lower bounds tight? Okay, can we prove kind of tight lower bounds for this very natural polynomial? So it turns out that the upper bounds that we do have for this polynomial look slightly different. They are of the form n to the d to the 1 by delta for product depth delta. And now, while these expressions look similar, you can see that the dependence on delta is quite different, right? So this sort of the triple exponent here fades a little more gracefully as delta grows in the upper bound than it does in the lower bound. So there's a considerable gap between the upper and the lower bounds, especially as delta grows. It's a very natural question to ask: can we hope to prove lower bounds that sort of match this upper bound? Can we hope by the partial derivative technique to kind of capture the complexity of this very natural computational problem? Okay, so that's sort of the motivating question. And now I can tell you about our results. So our results are threefold. So for one, we give a combinatorial characterization of the best formula lower bound we can hope to prove using this technique. Okay, so especially in the low degree setting, which is where we are really where set multilinear lower bounds and general circuit lower bounds are related, we give a combinatorial characterization that captures the best formula lower bound we can hope to prove. So far I've been talking about circuit lower bounds, but in the small depth setting where these things are most interesting, circuit lower bounds and formula lower bounds are more or less equivalent. So we characterize the best formula lower bound that we can hope to prove. Okay. And so that's a nice combinatorial characterization. And now we, in the remaining results, we sort of put this combinatorial characterization to use. So in particular, for the setting of product depth 3, which is the first interesting case for us, we show that this combinatorial characterization can at best prove a lower bound of n to the d to the 1/4. And we show that in fact it can prove a lower bound of n to the d to 1/4. Now, this is interesting for multiple reasons, but the reason it's most interesting is that the upper bound for iterated matrix multiplication for product depth 3 is n to the d to the 1/3. So there is a provable gap between the best thing we can hope to prove using this technique and the best upper bound we have. Okay, so this is not completely positive news. So we would have liked to be able to match the upper bounds with our lower bounds, but this example seems to suggest that's not the case. But this example sort of, this result still leaves open the possibility that we can get the right lower bound up to maybe a constant factor in this triple exponent here. Maybe we can get n to the d to the 1/2 delta or something like that. Okay, so in our final result, we sort of say no to this more relaxed version of this question. We show that the best lower bound for product depth delta is sort of much worse than the upper bound. So the upper bound is something like n to the d to the 1 by delta, but the best lower bound is n to the d to the 1 by poly delta. In fact, worse, it's something like a super polynomial function of delta. Okay, so those are results, kind of negative results for the power of this technique in order to prove significantly stronger lower bounds than the ones we have. Okay, so let me start now by telling you a little bit about this combinatorial characterization that we have for this technique. Okay, so this is based on something called tree bias that we introduced in this paper. So again, we are looking at set multilinear polynomials where the variable sets in the variable partition have various sizes, and some of these are designated as gray and green in order for the partial derivative measure to be defined. Now, all this information can be packaged together neatly in a single set of signed numbers. Okay, so what is this set? So we take the multiset of numbers alpha 1 through alpha d, where each alpha I is going to be plus rho I, right? If xi is a gray variable set and it's of size n to the rho I, or it's going to be minus gamma j if xj is a green variable set and its size is n to the gamma j. Okay, so these numbers both capture the sizes of these sets, and their signs kind of capture whether they're gray or green. Okay, so this in the set multi-set W has all the information that is required to specify the space of set multilinear polynomials. So that's the intuition. And now, given such a set W, I'm going to define a notion of a tree decomposition of W. So what is this tree decomposition? It's something that we call a W tree. So at a high level, what this is supposed to do is supposed to capture how a formula can try to compute something that's full rank with respect to this notion of partial derivative complexity. Okay, and it's kind of trying to generalize the PIP example. So we are trying to say, oh, the PIP formula, the formula computing the PIP polynomial is one formula that computes something that's full rank with respect to a certain for a certain lopsided space. But now for a general lopsided space, we can try to generalize the PIP construction. And so how would we generalize this PIP construction? This is something that we're trying to kind of generalize the strategy of the PIP construction by defining this notion of a W tree. Okay, so what's the W tree represent? It sort of represents the multiplicative structure of the underlying formula. And for a suitable multiplicative structure, we're trying to understand what is the smallest formula size that is required in order to compute a full rank polynomial. Okay, so with that preamble, so let me just go ahead and define this notion of a W tree. So what's a W tree? So it's just a tree, the leaves of which are labeled by elements of the set W. Okay, so here in this case, I'm assuming D is 6, so this is the tree. Okay, and now given such a W tree, I'm going to define notion of complexity for this W tree. So what's this notion of complexity? Well, given any internal node or given any node U of this tree T, I can talk about the sum of this node. Yeah, and what's the sum of this node? Well, it's very simple. I look at the subtree rooted at this node, and I look at all the elements of W that appear as leaves of the subtree, and I sum them together. So that's the sum of any node U. And now, given this notion, I can also define what I'll call the bias of this node. Okay, so this is only defined for internal nodes. So the bias of an internal node U is kind of the sum of the absolute values of the sums of its children, right? So I sum over its children, I look at their sums, but I sum their absolute values, and I subtract off the sum of U. Okay, so it's not hard to see that the bias of U is a non-negative quantity, simply because the sum of U is the sum of the sums of its children. Okay, so just by triangle inequality, the bias of U is always a non-negative quantity for any internal node U. Okay, so that's a bias for an internal node. And now let me come to this notion of complexity of this tree, which I'll call the bias of the tree T. Okay, so what's the bias of T? So now I maximize over all paths in this tree T. So I take all paths in this tree T and I maximize over them. And for each path, I look at all the internal nodes that appear along the path, and I sum the biases of these internal nodes. Okay, so I sum this, and that sort of gives me the bias of the path, and I take the maximum bias of the path, and that's the bias of the tree. Okay, and sort of this tree is very complicated if its bias is large, and if its bias is small, it's sort of simple and it leads to small formulas. That's the intuition. Okay, and the tree bias of a set W is sort of the bias of the least complicated tree for this set W. Okay, so I can also do this with respect to a depth parameter delta. So a tree bias with respect to a depth parameter delta is the minimum bias. Okay, so it's sort of the tree that leads to the minimum sized formula in some intuitive way. Okay, so that's kind of a mouthful, and it's the notion of the tree bias of set W. So now let me just sort of illustrate this with an example. Okay, so let's take the set W, extremely simple, to be 1, -1, 1, -1. So d by too many ones and d by too many minus ones, so that this whole set W is balanced. Okay, so just going back to the partial derivative space or the set multilinear space this represents the space of polynomials where you have d variable sets all of the same size, right? N, and half of them are gray and half of them are green. Okay, so that's the space of set multilinear polynomials this represents. And now the question is, okay, what's the best, what's the bias of, what's the tree bias of this W? Okay, and I claim that the tree bias of this W is at most 2. Okay, so it's a very small number. It's independent of the size of the W, it's at most 2. Okay, so how do I prove this? Well, let's look at this very simple tree. Yeah, so it's just a depth 2 tree, and this is how I kind of decompose this the elements of the set W. Okay, so let's look at the bias of this tree. So how do I do this? Well, first what I do is I compute the sum of every node. I already have the sum of the leaves, so let me compute the sum of the internal nodes. So it's very easy to compute, they're all zeros. Okay, and now let me compute the bias of all the internal nodes. Okay, suppose I take a node at level 1 here. The bias of the node is going to be the sum of the sums of its children in absolute value, and I subtract off the sum of this. Okay, so that's going to be 1 plus minus 1 in absolute value, that's 1 again, and I subtract off 0, so I get a bias of 2 at each of these nodes. And doing the same thing at the root, you can easily see that I get a bias of 0 at the root. Okay, and so there's just a definition of bias again. So that's what we compute. And now you can sort of compute the biases of all the nodes here. So this is what we've done. And so the bias of the tree is the maximum or all paths in this tree of the sum of the biases along the path, and that's going to be 2. Okay, so this shows that the tree bias of this very simple set W is 2. Okay, it's at most 2. So it's an upper bound on the tree bias. Okay, and this should sort of remind you of the PIP example, because the way the PIP example computes a full rank polynomial is that it takes pairs of gray and green variable sets, takes the inner product, and then kind of multiplies them together. That and the multiplicative structure of that formula is sort of mirrored in this W tree that we have here. Okay, so it's sort of a one-to-one correspondence between the two. All right, so another interesting example is this one. So here I'm not going to prove it for you, but let's say I take a set W with a bunch of minus ones and a bunch of numbers which are something like this, and I take enough of these numbers so that the sum of this whole set is approximately 0, close to 0. Okay, and in this case, it's not hard to show that so this is the numbers of these sets. Okay, and in this case, it's not hard to show that the tree bias of W with depth parameter 2 is something like square root D. Okay, so that's the tree bias, and this is in fact the combinatorial part of the lower bound. So the combinatorial heart of the lower bound from LST21. This proves lower bounds for set-multilinear circuits of product depth 2, which in turn implies lower bounds for general algebraic circuits of product depth 1. Okay, so this is it's a nice exercise to get kind of comfortable with tree bias. All right, so the first result we prove kind of more formally in terms of tree bias is that we show that for any W, the size of the smallest product depth delta full rank formula. Okay, so if I fix W, the size of the smallest product depth full rank formula is captured by the tree bias of W. Okay, so at any depth, the best lower bound I can prove is something very closely related to a tree bias. This is true only in the low degree setting, but that's sort of what we're interested in, because that's where set multilinear and general algebraic circuit low bounds are related. Okay, so so it's a complete combinatorial characterization of the best low bound we can prove in terms of this tree bias solution. Okay, so how do we do this? Well, it's actually it's a little bit technical, but at a high level, very simple. For the upper bound, what we do is that we kind of generalize the PIP example. So given a tree with small bias, we sort of recursively compute generalized inner products and use this tree T as a guide for constructing our monomials. Okay, so that's sort of the very high level idea. I'm not going to get into details. And for the lower bound, what we do is that now a given formula doesn't have to come with a unique multiplicative structure, which is what we get in the upper bound. So what we do is first we break up the formula, any given formula for a polynomial in terms of a sum of formulas, each with their own individual unique multiplicative structures, each corresponding to a W tree T. Okay, and because D is small, the size of the sum is not very big, so this is not a huge blow up. And what we show individually is that for any multiplicative structure T, the corresponding formula Ft has low rank. Okay, so its low rank is bounded by the bias of T, and which is at least the tree bias by the definition of the tree bias. And now we use the multiplicative, the subadditivity of the rank in order to argue that the rank of the whole thing is small. Okay, so this is the basic structure of the proof of this theorem. All right, so that's sort of the first result. The second result, what we show is that so we then use this combinatorial notion in order to characterize the best lower bound we can prove at various product depths. So in particular, in our second result, we show that for product depth 3, the best value of the tree bias, the maximum overall W of the tree bias of W is something like D to the 1/4. Okay. And this has two components. We actually need to come up with a W where the tree bias is in fact D to the 1/4. And then we need to show that for every W, the tree bias is at most D to the 1/4. Okay. And the lower bound is sort of similar to the depth 2 thing that I told you about. Instead of taking alpha to be 1 minus 1 by square root D, we take something else. Yeah. And in particular, this leads to lower bounds of integral D to 1/4 for the iterative matrix multiplication polynomial, which is not known before. And it generalizes to larger depths as well, but it generalizes in a very bad way. Again, the lower bounds are the triple exponent drops exponentially with delta, so it doesn't really yield in general much stronger lower bounds than our previous result. Okay, so that's sort of the lower bound. For the upper bound, we actually need to show that given any W, the tree bias of W is at most d^1/4. And this is significantly more complicated. So I'm not going to tell you the proof of this, but it's an elementary combinatorial argument. And it's sort of based on a simple principle, which I can try to outline. So let's imagine for now that the set W was of the form that we have been using so far in order to prove our lower bounds. So let's say it contains a bunch of -1s followed by a bunch of alphas, and alpha is just some real number between 0 and 1. Okay, and so the basic fact we use is this theorem of Dirichlet. Yeah, so it's a kind of classical theorem in combinatorial number theory, or just combinatorics maybe. So what it says is that given any real number alpha and given any parameter t, there exist integers p and q less than or equal to t, such that the difference between q alpha and p is bounded by 1/t. So again, you can make these, you can give very, very good rational approximations to alpha as your numerator and denominator grow and allowed to be bounded by some large number. Okay, so this is Dirichlet's theorem. And the reason this is useful for us is that the existence of these p and q immediately apply that there is a subset w0 or w prime of w of size at most 2t, right? So I take a bunch of -1s and a bunch of alphas, and the bunch of -1s given by given by p, and the number of alphas is given by q. So I take a subset of w of size p plus q, which is at most 2t, such that the sum of the elements in the subset is at most 1/t. Okay, and I can use these subsets as a guide to constructing my W tree. So I take this subset and I kind of repeat this process, and I kind of partition W into subsets of this form, and then I combine them further together recursively and so on. So this is the basic idea behind the construction. Okay, so this is how the construction works when W has a certain special form of this kind. What about general W? Okay, so now if W is just an arbitrary multiset of numbers with no structure of this form, then what do? Well, we prove kind of a cute generalization of the Dirichlet principle. Okay, and as far as I know, this is new. I asked around in a few places. I could not really find a reference for it. So if somebody knows a reference, please do let us know. So the generalized Dirichlet principle, again proved in a very similar way to the Dirichlet principle, is the following. So we have given any multiset of numbers between -1 and 1, with a significant number of positive and negative numbers, we can always find a subset of this multiset such that the sum of the elements of the subset is bounded by 1/t. Okay, so this instead of it's a very similar statement to what we used already, but instead of applying to very specific kinds of W, this really applies to general W with some very weak assumptions. So we use this generalized Dirichlet principle in order to construct our W trees in more general settings. Okay, so that's the upper bound. And the third result, which is this kind of thing for higher depths greater than 3, is more complicated. There's a divide and conquer procedure. So I'll leave these details to the paper and for those who are interested. Okay, so I've come more or less to the end of my talk. So let me just conclude with a couple of open questions. So the first and most interesting open question is stronger lower bounds. So now we know that the lower bound techniques we introduced in our previous result cannot prove lower bounds that sort of match the best thing even at product depth 3. So now can we actually match the best thing, at least for iterated matrix multiplication at product depth 3? In the low degree setting, this is especially interesting. There has been recent work that has done this, but not in the low degree setting, in the higher degree setting. But in the low degree setting, this still seems to be open. Okay, so that's a concrete avenue for progress. And a more kind of a high level question is, can we get a similar combinatorial understanding of other complexity measures? So there are extensions to a partial derivative measure, the shifted partial derivative measures, and many other things. Can we get a similar combinatorial understanding of the kinds of lower bounds that they can prove? There are meta-complexity theoretic works in algebraic circuit complexity, but usually they work in more general settings, but for weaker computational models or rely on unproven assumptions. So maybe can we sort of get a trade-off where we are able to handle smaller kinds of restricted classes of complexity measures, but say something very concrete about fairly general models of computation. Okay, so that's a nice open question that I think our work suggests. So that's all I have to say. Thank you.